right, 9.4 has 3 sections or 3 pieces to it. It gets back into adding and subtracting with radicals, and that's part A. Part B is multiplying, using FOIL again. We haven't used FOIL in a while, but we're going to come back and use some FOIL stuff. And then finally, C is looking at rationalizing denominators. And so that's what we're going to do today. So 9.4a, which is addition and subtraction, of radicals. And when you look at addition and subtraction with radicals, what you must pay attention to is the variables must match and the radicals must match. So what in the world is all that stuff? Well, that kind of looks like 3x the square root of 4, or let me put something underneath there that we can't get a square root of. 3x the square root of 3 plus 7x the square root of 3 plus 2x the square root of 2. If that were my problem that I have, that I'm working with, I would look at this and say, all right, what do I have that matches? Well, in every one of these, the variable matches. Okay, at that part? Everybody's got an x. So if we were back in basic algebra, we would be looking at something that would have radicals in it, and we'd take all that and stick together, right? Because we could put 3 plus 7 plus 2 together, and we're good. But now when we put radicals in there, we have to not only look for variables to match, but we also have to look and make sure our radicals match each other. And since this is the square root of 3 and this is the square root of 3, these two match each other, but that one doesn't, right? I agree. So 3 plus 7, so now I'm back to doing my normal stuff with like variables and or like terms, because 3 plus 7 now match each other, and I get 10x the square root of 3. But this 2 needs to just come along, just like if we had a y sitting out in something that didn't match. And so this would be my answer that I would put into Hawks if I were putting my answer in that position. Okay? So this piece is what I would use in that spot. So from that, looking at that piece, that's what we end up doing with these, is you end up looking for stuff that matches within them to see if we can combine some things together. But they don't always have them completely solved for you. And that's where the problem comes in, because if we had 4 to the square root of 3 plus 3 the square root of 12, if I look at that one, it doesn't match very well, does it? Because stuff doesn't end up looking the same. So back in 9.2, where we just had this, for instance, we would have to look at that and say, can I break it apart and get it simplified and have it still be exact? Now, the simplifying is not taking the square root of 12 and just putting that in there, but it's taking a look at 12 and seeing if I can simplify it. Well, if I take 12 over here on the side of my paper, I get 4 times 3. 4 is made up of 2 times 2. So 12 is actually 2 squared times 3. We all agree? Okay. So that means I can pull a 2 out. When I pull that 2 out, I have 3 times 2, the square root of 3. We all agree? Okay. And 3 times 2 is 6, the square root of 3. We got that all right? So far, so good? So now if I go back to my original problem, then I can bring down with this that first part, and what do I have now? They match each other, okay? And because they match each other, I can stick them together. 4 plus 6 is 10. And the square root of 3 is acting like my common variable piece in here, but it's a common radical. And so therefore I end up with 10 to the square root of 3. Yes or no? You need the skills from 9.2 to do this stuff, because this piece right here is 9.2. because you worked with 9-2 to break stuff apart. And so you kind of got that piece in there to play your role with what you'd have to do with it. Now the other thing that they end up doing with these is they might give you something like 2x, the square root of 7x, plus 3, the square root of 28x cubed. So if they give you this one, well, is the first one, and you're going to go through and ask yourself, is that one broken down as far as it'll go? What do you guys think? Pretty much. Can't take anybody out, right? Because they're the way they are. But if I look at this one, that one I need to take over here and break it apart more. Because if I take 28 and break 28 to its prime numbers, I get 7 times 4, and 4 is 2 times 2. So that really means under my radical, I have 2 squared times 7x cubed. So far, so good? Yes, no? Okay. So what can I pull out? Well, I can pull a 2 out, so that means I have 3 times 2. I can, and that's going to leave a 7 under my radical for the moment. This x cubed, I can pull out a, what can I pull out? An x. Can I pull out, yeah, I can pull out an x squared from underneath here, but I'm taking out an x, right? And what does it leave me? Leaves me still an x underneath. So really, this whole thing is equal to 3 times 2 is 6, the square root of 7x. And what happens to them? Now they match, right? Oops, I need my x with my 6. I had it here. I just forgot to put it over there. Okay, so now they match. And so 2x plus 6x is 8x, the square root of 7x. And I'm done. Okay?
How did you take 2 out? How did you take 2 out?
My index up here, the question was how did I take the 2 out? My index is 2 because it's a square root. So 2 went into 2 once, which meant I could pull out a 2. 2 doesn't go into 7 to the first, so it stayed. 2 went into 3 once, so I can pull out an x, but it leaves a x. Okay, that's kind of that double thing with that dividing, where you gotta be careful with putting the 2 into the 3 and coming up with your value that you got out of there.
Now, if it were 4 squared, would there still be a 2?
Oh, if 2 were to the,
If it was 4 to the second power.
oh, then you'd pull out a 4. Because you're saying right here if it would have been 4 squared, right? Because 2 goes into 2 once, I still would pull out a 4. Okay? But if you had written a 4 here, okay? 4 is a perfect square. See, that's why you got to go back and look for perfect squares if you do it that way. And sometimes it's kind of cumbersome and kind of hard to look at that and say 4 is a perfect square. And pulling out a 2, where if you break it apart and you get all your exponents, then you can get your exponent part out of there. Okay? And then you're not stuck trying to figure out what in the world I got for perfect squares with that one. Okay? All right. Now, they do end up going through and giving you some things that have cubes in them. So, if we take a look at this one, the cube root of 40x plus 3, the cube root of 5x, minus 2, the cube root of 135x. So we've got cube roots in there. So now what am I looking for? I'm looking for things that have 3 items. Okay? Is this one broken down all the way? Nope. So I need to take 40 over here, and let's find out what we can get out of 40. 40 is made up of 8 times 5. 8 is made up of 2 times 4. And 4 is made up of 2 times 2. So the cube root of 2 cubed times 5. We okay? That's all that 40 gives me.
What about x?
Yep, and then I gotta bring my x down. Okay? So what can I pull out? I can yank a 2 out of there, right? So I'm left with 2. The cube root, can I pull a 5 out? No. Can I pull an x out? No. The neat thing about Hawks is it kind of gives you clues. The clues are in here that they'll give you something that automatically has the thing that you're looking for, all right? So usually that's kind of a clue to you that in some cases you're going to end up with these things. Can I do with anything in the middle? Nope. So I'm just going to bring it down, and I'm going to write 3, the cube root of 5x. Can I do something with 135? Well, let's see. 135. Well, automatically 135 ends in a 5, so what do I automatically know? Take out a 5. So 5 goes into 13 twice. 5 goes into 35, 7. And 27's made up of 9 times 3. And 9's made up of 3 times 3. We okay so far? Okay. So what do I have under here? I've got a negative 2 out in front. I have 1, 2, 3 3's. And I have a 5, and I have an x. So what can I yank out of that one? Pull out a 3. So I have a negative 2 times 3, the cube root of 5 I can't pull out, and x I can't pull out. So really I have a negative 6, the cube root of 5x. Yes or no? We good? What do I get for a final answer? 2 plus 3 is 5. 5 minus 6 is a negative 1, the cube root of 5x, because they all matched. Okay? So is this bad? This isn't bad, okay? Once you get that skill of doing this part and breaking these things apart from 9-2, these guys go pretty easy because you're looking for stuff that matches. Now, when you look for these that match, you also need to make sure that you have matching indexes before you put stuff together. This whole thing looks like I could just throw that whole piece together and be done with it, right? But I can't, because my cubes and my cubes have to go together. My square root's not like it, okay? And so my answer to this is 2, the cube root of 3x, plus the square root of 3x. So they do throw those in, so be real careful. It looks like they match, but when you look at indexes, they don't. So be really careful with combining and putting some of those things together. How about this one? 7, the square root of 72, minus 5, the square root of 2, minus 5, the cube root of 2. What's going to happen with that thing? And can I pull anything out of it? I'm thinking no, didn't have. So, see what you guys get. Can't break this guy apart, and can't do anything with that one, but I can do something with the 72 in there. Alrighty. Everybody get it broken down? What did you pull out? A 2? And we pulled out a 3. Yep. So then I need to take this piece that's in the front of here and multiply it together. 7 times 2 is 14. 14 times 3 is 42. Minus 5, the square root of 2, minus 5, the cube root of 2. So my final answer with this thing is 42 minus 5. So what's 42 minus 5? And can I take that 5 off of it too? No, because of that cube. Yep, and that's what you get for those. Not bad? Okay. If I find one that's got some letters in with it. I have a tendency not to get too carried away with putting a bunch of extra letters that you gotta solve underneath. How about this one? Let me flip my page over. 5, the square root of 4x, minus 2, the square root of x, plus 2, the square root of y. What's that one going to give you? These, again, are ones that just come up in practice. They're like the ones that come up in Certify, so they show up all over everywhere. What was that? That's a little bit. So is this one simplified all the way? No, because I can pull out a 2. So this is really 5 times 2, the square root of x, because 4 is a perfect square. Sometimes they give you perfect squares under there, and 4 is made up of 2 times 2. So even if you did break it to its prime factorization, you'd find you had a group 2, so they can come out. So I get 10, the square root of x. Can I do anything with this one? Nope, stays. Can I do anything with the last one? Nope. So my combination, can I stick anything together in there? 10 and a negative 2 becomes, nope, 8, the square root of x, plus 2, the square root of y. And that's your answer to that one. Alright, so not too off the bed. We need to do more. Are we okay? What do you guys think? Can handle it? Okay. Just be careful with subtractions to remember that they're negatives and that you're going to have to subtract them from what you got going and not add them in there to what happens to be. One last one. Negative 5, the square root of 96, plus 2, the square root of 25 x. You'd probably look at that one and say, can't do much with it, can't combine them at all. But Hawks will still ask you to simplify it. So we still got to get it down to its simplifications and what we can pull out of them. How do I know I can't combine these? They're not alike. That x made them completely different than each other. Okay? So they're not the same. So you would take your 96 and break it apart. Well, it ends even, so I know 2 goes into there. 2 goes into 9 4 times and goes into 16 8. 2 goes into 48 24. 2 goes into 24 12. 2 goes into 12 6. And 2 goes into 6 3. So what am I left with? 1 2 3 4 5 2's times the 3. So what can I pull out of there? A 2 squared, right? Negative 5 times 2 squared. It's going to leave a 2 under here and a 3, right? So I really have 4 times a negative 5 is a negative 20, the square root of 6. And then if I simplify the second one, 25 is a perfect square, so what do I pull out? A 5. So plus 2 times 5, the square root of x. 2 times 5 is 10, the square root of x. All right. but I can't stick these together at all because they don't match each other. Okay. And they wouldn't match regardless if this x wasn't there, because I'd had nothing left underneath that radical, and I'd have to have a 6 in order to combine them. So they can't be put together. Okay?
If it was a 6 action, right? Or if it was just an x.
If this were just an x, if this would have just been an x right here, it would have to be identical. Okay? They've got to match perfectly in order to put them together. Okay? So if this would have had a 6 with it, it still would not have matched because it's got an x. I would have to have a 6x in both to put them together. Okay? So they have to be, they're no different. This radical piece is no different than saying you have an x here and a y there. They're that different. They make it, they're like a letter, but they're signifying that the two are different and they don't match each other. Okay? So you want to make sure that you got your pieces in there that match each other. Okay. We're good with this then, you think? Okay. I see heads out there shaking. Yes, we are good with that. 9.4b. B is multiplication and division. Well, it's actually multiplication. And in multiplication with radicals, we are going to use FOIL. So let's review what FOIL did for us. FOIL meant multiply the first, multiply the outside, multiply the inside, then multiply the last. Okay? And so that's what our FOIL meant. And so if we review that and we have 3x plus 2 times 2x plus 1, we just simply put 3x times 2x and ended up with 6x squared. 3x times 1 is a plus 3x. 2 times 2x is a plus 4x. And 2 times 1 is a plus 2. Then we needed to combine our centers together. So I got 6x squared plus 7x plus 2, and I left it at that. And of course, until we made it to chapter 6, where we foiled it, or not foiled it, but we took a look at this and we factored it and came back to what we started with. All right, but right now that was the piece that we did with that. Okay, now the difference with radicals is that, of course, you're going to have radical pieces that are involved with this foiling. So to start out, and maybe in a little simpler manner, we're going to multiply by a monomial first, and a monomial, of course, means a single term. So if I had the square root of 3, and I'm going to multiply that square root of 3 times 2. So if I multiply square root of 3 times 2, that just simply ends up being 2 to the square root of 3, because I can't multiply the exponent in front of here. I'm multiplying the numerical 1 times the numerical part. Okay, I multiply the radical part by the radical part, but I don't have a radical part in this one, so my answer just comes out to be 2 to the square root of 3. We okay with that part? So that's kind of like what we did in the last section when you pulled out that 2. Remember when we pulled out the 2 and we had the let's see, what was it? Was the 90, or if we pulled out the 4 out of a square root of 20, and you had a 4 out here, you pulled out that 4, you took 4 times 4, or 4 times 2, I should say, and you had the square root of 5 left over. So it's kind of like that kind of multiplication, where I multiply the numerical part, but I don't do anything with the radical part. Yes or no? We good? Okay. Now, if I have the square root of 3 times the square root of 5, for instance, what in the world does this mean? Well, back in, let's see, what section? I think it was section 9.2, we were able to take a number and break it apart. Remember how we took that number and we broke it into 2 separate pieces? Same kind of thing happens here. I multiply the numerical parts under my radicals together. So 3 times 5 is 15, and my answer comes out to be the square root of 15. We all right with that part? So I took 3 times 5, and I end up with 15. Now, when I do that, my indexes, these two pieces, have got to be identical. They got to match each other, or I can't do it that way. If they do not match, then I'm in 9.3, where I had to come up with fractional values and multiply and add my fractions together to do it. In 9.4, these will always match. You don't have to worry about getting cubes and a square or anything like that. They will match each other, so be aware of that they're gonna be the same when you do that. So you get that piece going with those. So then if you have the square root of 3 times the square root of 3 plus 2, so now I just kind of put my two things that I was doing up above kind of together. Square root of 3 times the square root of 3, what does that give me? Well, that gives me the square root of 9. And what do I know about square root of 9? Square root of 9 is 3, right? It's perfect square, 3. So what happens when you multiply like indexes with like radicans? So like indexes on like indexes of a square, or of a 2, in other words, the radical disappears or is removed, and the radicand is a whole number. So basically, a square root of 3 times the square root of 3 leaves me a 3. You can write it this way if you want, put the 9 under there if you need to have that security of knowing what you have. Or you can also write this as 3 times 3, and we know when we have pairs of 2 things underneath, we pull it out, right? And so that's where I get my 3 at. But when I multiply the square root of 3 times 2, I get 2 the square root of 3. And so that part doesn't get combined at all. It stays separate. Alright, so what if I have the square root of 5 times 2 the square root of 5 plus 4? And what's... Oh, this final answer on this one? Oh, sorry. Is 3 plus 2 the square root of 3. Because square root of 3 times the square root of 3 is 3. Square root of 3 times 2 is 2 the square root of 3. And so my answer comes out to be 3 the square root, 3 plus 2 the square root of 3. Alright? So what happens with this thing? Square root of 5 times 2 the square root of 5. So I have 2. Square root of 5 times square root of 5 is just plain old 5. Yep. Plus square root of 5 times 4 is 4 the square root of 5. So 2 times 5 is 10 plus 4 the square root of 5. And that's my final answer. Okay, I can't do anything else with it.
So when you have like the radicals are the same, so the radical eliminates itself.
Yep, just drop it. Now, be careful with that because it only works with squares that you drop it. If I had a cube and I had 5 under here and I had the cube root of 5, if I had the cube root of 5 times the cube root of 5, this does not remove because this only gives me the cube root of 25, but 25 is not a perfect cube, right? So we have to be careful with cubes. But they don't give you any cubes in this piece. They only give you squares, square roots. They won't have any cube roots with this part. So it's only squares that you're working with this piece. Okay? We do get into looking at this in the last part when we rationalize the denominator in 9.4c, but we don't use it in this 9.4b at all. Alright? What do you guys think? So far so good? Okay. So, we've taken a monomial times a binomial. We've taken a monomial times a monomial. And then when you take a binomial with a radical in it times a binomial with another with a radical in it, what's going to happen to this thing? Well, I need to do my FOIL. So the first term times the first term is going to be the square root of 3 times the square root of 3 is going to be 3. Now, if you get so you automatically recognize that, you don't have to write the square root of 9 and all that good stuff in there, okay? When these match each other, indexes are the same, the radicand underneath is the same, and they're squares, I can just drop my radical sign, all right, and take what's underneath it. Square root of 3 times a negative 3 is a negative 3, the square root of 3. We all okay with that part? Yes? Okay. Now I'm going to do my 2 times the square root of 3, so that's a plus 2, the square root of 3. And then finally 2 times a negative 3 is a negative 6. So then what I need to do is go back and combine like terms. And in some of the cases when you combine like terms, you may only end up with 2 terms when you're all done. That seems kind of foreign because we're used to seeing 3. We're used to getting a trinomial piece out of these, and sometimes you don't. Because 3 minus 6, these match, correct? Straight numbers. 3 minus 6 is a negative 3. Negative 3, the square root of 3, and a positive 2 square root of 3 leaves me with negative 1 square root of 3. Okay?
I got it before you. I'm good.
And Hawks is probably not going to like you putting the 1 in there. Okay? So when you put this in Hawks, it's going to be negative 3, negative square root of 3. All right? They know there's a 1. You know there's a 1 there because any variable, this again is acting like a variable, and although it's a radical, you got a 1 in front of
They
there.
don't like ones.
They don't like ones.
When you're doing slope intercept,
Yeah.
you put a 1, negative 1x, it's not right.
No, they don't like
They
it.
want just the
No,
negative.
they just want the negative in front of there. Yep. So let's do another one of these. 2 the square root of 11 minus 5 the square root of 11 plus 2. So what do we get out of this whole thing? So first term times first term. So what am I left with? I'm left with 2 times, because 2 is times the 1 in front of this. Square root of 11 times square root of 11 is 11. 2 times 2 over here is a plus 4, but I still got that square root of 11, just like if I had an x on there, it still comes along. Negative 5 times the square root of 11 is a negative 5, the square root of 11. Negative 5 times a positive 2, or negative 5 times a positive 2 is a negative 10. So then I need to clear out a couple things in here because 2 times 11 is good old 22. 4 minus 5, these two match each other, so I have a minus the square root of 11 minus 10. But I'm not quite done yet because 22 needs to be combined with the negative 10. So my answer is really 12 minus the square root of 11. All right. Now you might be able to get done with this a little bit faster than what I'm doing it because you might take this in your head, get 22, take 10 away from it, get 12, and then combine those two together. So there's some combining of stuff that you can end up doing to make them a little shorter when you start writing them on your paper. They do give you ones that look like this too, the square root of 6 plus the square root of 3, and they put a square outside of it. Now when we had those back when we were multiplying just regular straight binomials with no radicals in them, what did that mean? What did I have to do to that? Double it, right. I need to write it twice. That does not mean I square this and I square that and I'm done, right? That means I have the square root of 6 plus the square root of 3 times the square root of 6 plus the square root of 3. So I need to see it twice in there to FOIL it. So square root of 6 times square root of 6 is 6. Square root of 6 times square root of 3 is the square root of 18. We all agree? Square root of 3 times square root of 6 is another square root of 18. And then last of all, square root of 3 times square root of 3 is a good old plus 3. And it looks like, well, all I got to do is put 6 and 3 together and I get 9. One of these and one of those gives me 2 to the square root of 18. Okay? But if I type that into Hawks, what's Hawks going to tell me? Not simplified. Not simplified. Okay, so it's not simplified, and I'm thinking, well, 9 is simplified, but this 18 is not. Okay, so then you need to take 18 and break it apart to 9 times 2, and 9's made up of 3 times 3. So really, I have 9 plus 2 to the square root of 2 times 3 squared, or I can pull out a a 3, right? 9 plus 2 times 3 to the square root of 2, or I have 9 plus 2 times 3 is 6 to the square root of 2. So it's going to tell you it's not simplified. All right, so be careful with that. That you got to break everybody down to their lowest of what they could possibly be. Yes?
Would it be wrong if we added the 9 and 6 together?
Yes. They do not match. That is just as nasty of adding those two together as adding 9x plus 6y. Okay, same thing, just as bad. So, yep, be careful. If this does not have that root, they do not match. They are different as night and day. Okay, because this is a solid 9. This isn't solid. This is saying I got 6 times whatever the square root of 2 is, and that's going to be a big decimal number. So be careful with those and make sure that you got your pieces together in there. All right, let's see what we can do for another one of these. How about this one? Square root of 2 minus the square root of 3 times the square root of 2 plus the square root of 3. What happens to it? So I have the square root of 2 times the square root of 2. First off, what should happen to it if you look at that one? There's something special about it.
Wait, hold on. The 3's
The 3's
go bye-bye.
go bye-bye? Is it the 3's that go bye-bye? Or is it something else that goes bye-bye? What was that? The signs? The center. Yeah, the center piece will go bye-bye when I foil this. Because notice these are opposite, but everything else matches. So way back when we found that with conjugates, back in basic algebra, that if we multiply this stuff together, the middle goes away. But with these, also something else goes away. All the radicals will go away. Okay? Every radical that's in here will disappear. Square root of 2 times square root of 2 is 2. Square root of 2 times that is a plus the square root of 6. Negative times this is going to be a negative square root of 6. And a negative 3 times this one, a negative times a positive is a negative. Square root of 3 times square root of 3 is 3. So what am I just solidly left with? These disappear. 2 minus 3 is a negative 1. So my answer is simply a negative 1. So things that have special abilities in there make differences. We use this when we do the last section in 9.4c because we're going to make denominators not have radicals in them at that point. So how about this one? 2 the square root of 2 minus the square root of 7 and 2 the square root of 2 plus 5 the square root of 7. How about it? What in the world's going to happen to it? So see what happens. It kind of fits that same kind of like the one up above, but the problem here is they're not identical to each other. So let's see what happens to it. We'll still have a middle term in this one because they don't match exactly. So multiply it out, see what you get. Then you just use FOIL with it. So you go through and do your multiplications in there and get your pieces to come together. Okay or not okay? Alright. One more, or you have enough? Another one? Okay, let me find one that's got letters in it. So they do give you those too. Square root of 3y plus 3 times the square root of 3y plus 2. See what happens with that one. Treat your letters the same as if they were numbers. So you're going to still, in this case, when you multiply that first thing together, what do you get? What are you left with? 3y. Right, because your radicals will disappear the same as they do with your numbers. So with letters, it's no different. And then you FOIL, of course, multiplying the second one. Oops, 2. 3 times that is going to be a plus 3. So really the math in these are not really that difficult because you don't have a whole lot of stuff you got to work on. 3 times 2 is 6. Cannot combine the 3y and the 6. Can combine the 2 and the 3. 5 out of 6. 5 is square root of 3y. But I can't put the 6 in there, so 6 comes down. This one came out to be a trinomial when we were all done with it, but the other ones don't. So some of them do, some of them don't. Some come out as one answer. Okay? Alright. Okay, last piece. And that is 9.4c, and this one is rationalizing a denominator. And when you rationalize the denominator, what that means is removing the radical sign from the denominator. Meaning I don't want any radicals in my denominator at all. And what we found out in this last part that we just got done doing is that if I take the square root of 3 times the square root of 3, what happened to that? Well, square root of 3 times square root of 3, remember every time we saw those, we ended up with just plain old 3, because the square root of 3 times the square root of 3 is really the square root of 9, which is 3. So therefore, when I rationalize that denominator, or not denominator, but when I take these two and I multiply them together, it automatically removes the radical sign. Okay? Now, if you had a fraction, and that's what a lot of these end up looking like, the square root of 2 over the square root of 3, if that were my problem, and I want to get rid of this thing in the denominator, what I want to do with this is I want to make this a perfect square down there. So in order to do that, if I found out up here, if I multiply square root of 3 times square root of 3, it got rid of my radical, what's going to happen down there? Well, with fractions, as we found that if I had 1/3 and I multiply the bottom by 3 and the top by 3, I end up with 3/9. Is 3/9 the same as 1/3? And we learned way back in basic math that these two are identical to each other. So as long as whatever I do to the bottom, I do to the top, I keep everything the same. You guys got that? So What would I have to do to this piece? Well, if I multiply the bottom by the square root of 3 and the top by the square root of 3, what happens? Well, it causes the top to be square root of 2 times the square root of 3, which is really the square root of 6. But the square root of 3 times the square root of 3, what happens to those? Long gone. And so I get 3 for my denominator. And I've rationalized my denominator because it no longer has any radical values in it, right? It's all solid straight numbers. Okay, so if I have the square root of 5 over the square root of 3x, what would I have to multiply top and bottom by to get rid of this? So I'd have to multiply it by 3x, the square root of 3x, correct? So what would I end up with? I'd end up with 5 times 3 is 15x under radical. And in the bottom, 3x times 3x is really just plain old 3x when I rationalize my denominator. And so that is that value simplified to its lowest terms. So I've kind of gotten rid of what that denominator happens to have in it. All right? Make sense? So far, so good? Hopefully? Yeah. Yes, unfortunately it does. Because what happens with these is they may have the cube root of 5 over the cube root of 2. Now the reason cubes get a little more difficult is because if I just simply multiplied this by the cube root of 2 and the cube root of 2, kind of looks good, doesn't it? But when I do that, what happens? 5 times 2 gives me the cube root of 10. That looks good. But the cube root of 2 times the cube root of 2 doesn't remove the cube. No, it only gives me the cube root of 4. So that didn't help me out at all. I still got that cube in the denominator. You okay with that part? So what should I really multiplied it by? Well, this, in order to remove this cube root down here, has to be a perfect cube. So what do I currently have? Well, I got the cube root of 2 to the first power. In order to pull this 2 out, as we've found in all of the other stuff we've been doing in Chapter 9, what did I have to do? This has to be what? It has to be a 3, correct? How in the world am I going to make it a 3? Well, I'd have to multiply this by the cube root of 2 to the second. 2 squared. So if I multiply these two together, that gives me the cube root of 2 cubed, because exponent-wise, I can add these two things together under here. 1 plus 2 is 3. The cube root of 2 cubed is 2. Okay? Yes or no? Yeah, kind of shaky there, huh? Okay, and again, I understand that if the cubes are shaky, we're going to work with some other ones and try to figure out what we got to do before we end up trying to stick it together like we did here. To finish this one, though, just so that you do have it, and we'll do some more work with cubes, I would have to multiply the top and bottom by the cube root of 2 squared. So when I do that, this becomes the cube root of 2 cubed, or 2, but what's on top? 2 times 2 is 4. 4 times 5 is 20. So I would have the cube root of 20 on top. All right? But let's do some more balancing out with cubes and get some figuring out what we got to do with those things to make them work out. So what if I had this one? What would be its value we'd multiply it by if I had the cube root of 3 squared? What would I multiply that one by? What was it, B? 3 squared? You guys agree? Well, this is already a 2. What should it have to be? What should I make it be? I should make it be a cube, right? I should make it be a 3. So if I make that a 3, what would I have to multiply it by? Really, I had to multiply it by 3 to the first power, correct? because then what would happen is I would have 3 cubed under there because 2 plus 1 is 3, and that would equal 3. Yes or no? Okay. What if I had the cube root of x squared y? What would I multiply it by to remove my cube? I would multiply it by an x and a y squared. Yep, an x and a y squared. And when I do that, I get an x cubed and I get a y cubed. We all okay with that part? Yes? Kinda? Got head shaking out there good. We got some good stuff going. So this would end up simply being xy when I took the cube root of it, because what I would have had under here is x cubed, y cubed, and then that would have pulled out as an x and a y. Alright? So what if I had the cube root of 16, and I need to figure out what in the world can I do to get rid of that radical piece? Well, 16, I need to break it apart, right? Because 16 is not simplified, if you take a look at what Hawks does. 16 is made up of 4 times 4. And these break down to 2 times 2, and this becomes 2 times 2. So really, I have the cube root of 2 to the 4th power under there. What would I still have to multiply it by to get rid of the radical? So I could pull out a 2, and that would give me the cube root of 2. So what would I have to multiply it by to make it go away? Because 3 went into 4 once, so that means I can pull out a 2, but leaves a 1 of a 2 underneath, leaves a 2 underneath. What would I have to multiply it by? And I have 2, the cube root of 2. What would I have to multiply this by to make that root go away? A 2 squared. Perfect. Thank you, William. 2 squared. Yeah. So I have to multiply by 2 squared. So then what would my final answer be? My final answer would be 2 times 2, or 4. Okay? Now, could have I looked at this right here? Sure. They matched each other. And I could have said, I have the cube root of 4 squared. So what would I have to multiply it by? Cube root, just a 4. Okay? So wherever you happen to see your piece that you would have, that's what you'd come up. Notice I still got the exact same answer of 4 when I did that. So you got to be careful and watch for pieces that are going to make those perfect cubes. Yes or no? More? Should we do more of those kind? Okay. Another one might be the cube root of 12 x squared y. That was kind of a difficult one. I don't even know if they give you one quite like that in Hawks at all. But what has to happen to 12? 12 needs to become 4 times 3, and 4 becomes 2 times 2. So really underneath this I have 2 squared times 3x squared y. What would I have to multiply that by in order to get rid of my radical? Well, I'd need, remember, everything in here has to become a 3. So what would I need with this 2? I'd need a 2, right? I would need 3 squared. I would need x, and I would also need y squared. Yes. And if I multiplied all that by what I originally had, I could get rid of the whole thing and end up with 12xy when I'm all done. And that's what would come out of this. Because I would pull out a 2. Oh, no, I would have a 6. How am I getting a 12 in there? It would be a 6. Sorry about that. I pull out a 2. I would pull out a 3. I would pull out an x, and I would pull out a y. So yeah, it would be a 6x y, not a 12. Okay? Make sense? All right, now what happens with these is they give you something on the top. So on the top of this one, we'll just go back to that cube root of 16. And on the top, they might give you, let's see, we'll put a 4 in there. So what did I multiply this thing by? Well, I broke the 16 apart, right? And I came up with 2 to the 4th, or I came up with 4 squared, whichever way you want to look at it. So 4 squared. What did I have to multiply the top by? Cube root of 4. You okay with that part? Because all I did was break that part apart. I don't want to lose somebody on this thing. So cube root of 4 times the cube root of 4 is really the cube root of 4 squared, or the cube root of 16, all over 4. Now, what would Hawks tell you about 16? You can put it in there, and Hawks is going to automatically pop back and say, not simplified. 16, remember, broke down to 2 to the 4th power. And I kind of ran out of room here. So really, this is 2 to the 4th power all over 4. I can pull out a 2. Let's go over here in my little space I've got. I can pull out a 2, so it leaves me 2, the cube root of 2, all over 4. Is that simplified all the way it can be simplified to? Yes or no? No, because 2 and 4 will cancel. So really I'm left with the cube root of 2 over 2. And that would be my answer to this one. All right? I know this is kind of all over everywhere, but we'll get some more of those that aren't all over everywhere on my sheet. Okay, let's do some more with some cubes. About this one. 9 over the cube root of 16y. We'll still stick in the 16s and see what we can come up with. So, what would I have to do? Well, this is equal to 9 over the cube root of 4 squared y. We agreed last time because 16 popped up. What would I have to multiply it by? The cube root of 4 and a y squared. Yep. And so what would I be left with on the top? Well, I can't put any of that together, so 9, the cube root of 4y. The bottom is going to give me 4y. And can I put that into Hawks? Will Hawks be happy if I plug that in? Hawks won't be happy? Oh, thanks. Yep, I need a square. Thank you. Yep. Nope, because when I put this together and this together, remember that's going to be 4 cubed y cubed. And when I take the cube root of it, I'm going to pull out just the 4 and the y. Yeah, the cubes are always the tougher ones to take a look at. When you got a square, those aren't so bad. 7 over the square root of 3. What would I have to multiply top and bottom by? Square root of 3. And that simply is going to be 7 times 1 is 7. Square root of 3. And in the bottom, I'm just left with a single 3. So in that case, there isn't anything there to work with those. But the cubes tend to be the ones that give you more trouble than just the plain straight ones. They do, once in a while, toss in a 4th power. See what this one came across for me in my practice. Was the very first problem they gave me in that section. I'm like, huh? Where do we get a 4th power, 4th root out of? What would I have to do? What would I have to multiply this by? Well, it's kind of straightforward. There's no breaking this part down, so what would I have to multiply it by? 3, what was it? Squared? Nope, 3 to the 3rd power, yeah. Yeah, 3 to the 3rd power. And when I do that, this looks kind of like maybe I might be able to get something broken down out of there. What do you think? 144. Might be. The bottom comes out really easy. That's just plain old 3. But this top part, so if I take 144 over here, break it to 12 times 12, 12 breaks down to 2 times 6, and 6 breaks down to 2 times 3, and the same over here. So really, what do I have underneath this radical piece on the top? And I'm going to need more room, so I'm going to write it down here. Fourth root, 1, 2, 3, 4 2's, 1, 2, 3's, but then I got this thing out there. So what can I yank out of that? Can I pull anything out of there? Well, I'll put these guys together. That gives me the fourth root of 2 to the 4th times 3 to the 2 plus that is 6. So, oh, it's 3 to the 3rd. Thank you. Yep, and that would be the 5th then. Yes, it was a 3 from up there. That's where I got it at. Okay. Thank you for catching that. Okay, then what can I pull out? Well, I can pull out 2. It's going to leave a 2. Oh, no, it's not going to leave a 2. There's not going to be any 2's left. And I can pull out a 3, leaving a 3 to the 1st underneath my radical all over 3. These 3's cancel. Oops. And that just leaves me with 2, the 4th root of 3. Okay. So that's the long way with this thing. That's kind of the roundabout way out of whack. Long way. Hawks doesn't necessarily show you the short way, but I'm going to show you the short way. The short way on this thing is way back in 9.2. I could stick this whole thing under one radical because my index is matched. Remember that? So if I stick the whole thing back under this, what happens is, and when you run across these, when you've got cube roots, and if you've got something that cancels in there, you can do that. So canceling here, notice in my 144, when I broke it down, I had some 3's in there. So that meant 3 goes into there and 3 goes into here. 3 will go into 144. What was it, 48? Okay. And what happens to my denominator? Long gone. Okay. Do I have to rationalize the denominator now? Nope. It's gone. Okay. So I don't have to negotiate it, or I don't have to get rid of it. So this is the shortcut, all right? But it's only if they cancel. Because if you went back to this one that we have with the 9 and the 16, of course there's no radical on the top, but they wouldn't cancel, okay? Some of those, they do cancel. Other ones, they won't cancel. And I think, let's see, back here, when I had this one, would that have canceled? Yeah, you bet. Because what would have happened here is if I would have taken that problem and put 3 the square root of, or cube root of 4 over the cube root of 16, if I put this all back together, what happens? The 4 and the 16 cancel, correct? That leaves me with the cube root of 1 over the cube root of 4. I still have to rationalize this one though because the denominator did not disappear. Alright? But when I rationalize it, I'm just going to multiply it by the cube root of 4 squared. And so what I'm left with in the top is the cube root of 16 all over 4, and I'm done with it. Alright? Makes it a little easier. So if you run across these that are monomial over monomial, you can just simply reduce those. Put them back under the same radical, reduce them, okay? So that makes that part a little bit easier. So always look for that if you can end up canceling some stuff out in there with those. The last kind that's in here is when your denominator is not a monomial, and these are only with squares. They never give you cubes. And these are what we end up using the conjugate on. So find the conjugate of the denominator. And the conjugate, remember, is the opposite sign, but everything else is the same. So, my conjugate is going to be 6 minus the square root of 3. So I multiply top and bottom by it. And now you're back into the first part that we did when we multiplied our 9.4b, because I just take 3 times 6 is 18. 3 times square root of 3 is minus 3 the square root of 3. And in the bottom, because I know what's going to happen with my conjugate, what do I just have to multiply? I have to multiply first terms together. 6 times 6 is 36. Last terms together gives me a minus square root of 3 times square root of 3 is 3. So my final answer is 18 minus 3 the square root of 3, all over 36 minus 3, which is 33. But you type this whole thing into Hawks, and Hawks is going to come back and say, wrong. No, it's going to come back and say not simplified. And it's not simplified because notice in these numbers, 18 and 3, you can pull out a 3. 6 minus the square root of 3 when I pull out my 3. 3 out of 18 is 3. 3 out of 3, the square root of 3 is square root of 3, all over 33. These cancel. So my true answer is 6 minus the square root of 3, all over 11. So you have to go back and simplify them. So you can't leave them not simplified. They give you that simplification back in 9.2, but they don't give you any problems to practice with it. So I didn't cover it in 9.2 because they don't give me any problems. I contacted Hawks, so next year will probably be in there. But for us, there's no homework problems that did it. But you're just pulling out a 3 because they can factor out a 3 right here, out of those. Okay, let's do a couple more of those so you get an idea of what goes on with conjugates. 8 minus x all over the square root of 8 minus the square root of x. So what is my conjugate with this thing? Square root of 8 plus the square root of x. Okay. So now I am simply to my foiling stuff. 8 times the square root of 8 is 8 the square root of 8. 8 times the square root of x is 8 the square root of x. X times the square root of 8 is a negative x the square root of 8. And x times the square root of x is plus x the square root of x. No, minus. Get my signs in there. You okay with that foiling? Can I stick anything together in there? Yes or no? Now these two look like they look alike, but they're not alike because this has an x and that has no x. Okay, so they don't match. These don't match because this doesn't have an x and that has an x, so that's all you can do with it. You can't put anything together in that one. And that happens sometimes when you are foiling back in 9.4b as well. You might have stuff that doesn't combine together. Bottom, square root of 8 times square root of 8 is 8. Negative times a positive is a negative. Square root of x times square root of x is just simply x. And I am all done because I can't do anything else with that. So that one's kind of got a lot of stuff in there with that one. But I guess they end up going a little farther with this one. If I look at my answer in there, they put these square root of 8's together. So 8 the square root of 8 minus x the square root of 8 plus 8 the square root of x minus x the square root of x. And they look at this piece and they pull out a square root of 8. Leaves me with 8. That's back to that 4 combination factoring way back when in chapter 6, I guess it was. So that comes out to be this. Then if I factor this piece by grouping those two together and these two together, I can pull out the square root of x. And that leaves me with 8 minus x. So really on top I have 8 minus x, and they do not give you very many of these. Square root of 8 plus the square root of x, all over 8 minus x, then the 8 minus x's will cancel out. And so your true answer is the square root of 8 plus the square root of x. So that one's kind of a long, drawn out, roundabout one. So if you get one of these in practice, that's why I'll mark you wrong if you type this whole thing in. So you got to regroup this stuff and factor out the stuff you can out of those. So be careful with those. I guess you could have left it as it is, because if you left it here, you could pull out your 8 and leave your square root of 8 and your x, and pull out your x over here, negative x, and you still would have had it. So if you get 4 and you get a denominator, take another look at it and see if you can pull something else out of it for those. Okay, what do you think?
Do another one.
Another one like this one? I don't know if, I think I only had one. I don't think they ever gave me another one anywhere else. See, that's the thing I have sometimes with, they didn't give me another one. There was only one. Only one showed up, but we'll do another one that's still got some stuff in it. I find one that's got a lot of the ones they give you in the practice are not ones that you have to foil with. They are basically ones that do not have that. So let's do this one. Negative 1 all over the square root of 6 minus the square root of 7. So Mary Jo, that was my only one that was long like that. Okay.
That's the same one that'll be there.
Yeah, it's kind of like that triangle one from basic algebra that popped up all over everywhere. So I need its conjugate. So what's this thing's conjugate? Uh-huh. Yep. And so negative 1 times this is a negative square root of 6. Negative 1 times that is a negative square root of 7. And then in the bottom, square root of 6. Square root of 6 is 6. Negative square root of 7, square root of 7 is 7. So this comes out to be a negative square root of 6 minus square root of 7 all over negative 1. And remember, Hawks does not like negatives in the denominator. So if we multiply top and bottom by a negative 1, I get the square root of 6 plus the square root of 7 all over 1, and I don't need the 1 in the denominator when I type it into Hawks. So that would be my answer to that. But it's that conjugate thing that you got to watch with these and getting your multiplications through. All right, anything else we got? You okay with this part? Hopefully. Okay.